All right, so we're going to dive into the second part of the limits intro notes. But first I wanted to do this warm-up, which is find the average rate of change for f of x equals the square root of x on the interval a to a plus h. And again, this is going to be flexing on our algebra skills, perhaps even hitting on something that some of you haven't seen before. So let's work through this together. If you want to try it on your own, go ahead and pause the video. We know average rate of change is going to be f of b minus f of a over b minus a. So in the case of our interval a to a plus h, what that means is we're going to have the square root of a plus h minus the square root of a over quantity a plus h minus a. And when we execute this problem here, we can see the first simplification is pretty obvious, and that's the simplification of the denominator. But as we learned yesterday, or in the prior notes, the ultimate goal is to see what happens as h approaches 0. And in this case, if I were to say let h be 0, I would have a divide by 0 error. So that's the reason that we are going to try to simplify this expression further. And the way we go about simplifying this expression further is we multiply by the conjugate of the numerator. And this is something that was taught early on in the pre-calculus curriculum, but a conjugate is, in this case, root a plus h plus root a. Now, if we are to do that to the top, then we must also do that to the bottom. That way we're effectively multiplying by a 1. And if I take the time to FOIL the numerator, my first terms multiply together to cancel the radical. My outer terms multiply and cancel with my inner terms. So these two multiplied is a positive version of these two multiplied, so they cancel out, and then we're left with negative root a times positive root a is negative a. Now, upon first inspection, this does not look any cleaner. But if we cancel the a's in the numerator, we see that now we have that case where the h cancels out of the numerator and the denominator, and I'm left with the expression 1 over root a plus h plus root a. Now, normally we don't like the idea of having radicals in the denominator, but the benefit of this method is that if I were to let h be 0, because ultimately that's where we're heading, I do not have a divide by 0 error. So when I, in the future, take the limit as h goes to 0 of this expression, the idea that your average rate of change is going between two closer and closer points, I wind up getting 1 over 2 root a. Now remember, this portion here is not what we're asking in the problem. This is the connection to why we're learning limits in the first place. Our motivation is we learn average rate of change, and then we are going to say, well, what's the average rate of change over a very, very narrow window of space? And we get to this. All right then, so let's dive into the notes where we left off in the last video. In the last video we finished up example 3, and we're looking at the limit as x goes to 5. In comparison to our warm-up problem, our warm-up problem has two variables, a and h, but in this expression we only had the one variable. But one approach that you can take when you're talking about limits is to look at it graphically, and actually graphically it's pretty easy to evaluate a limit. Most of the time in class we're going to be looking at graphical, at least early on. One other approach that you can take is actually through the equation and taking a tabular approach. So we have the equation x plus 2, and if I were to evaluate 2.9, which is close to 3, 2.9 plus 2 is 4.9. If I get even closer to 3, 2.99, 2.99 plus 2 is 4.99. And on, as we get closer and closer to 3, we can see by these substitutions of values getting closer and closer to 3 that these answers appear to approach 5 from the left-hand side. Similarly, if we do it on the right-hand side, we are getting closer and closer to the value of 3, 3.1, and then closer is 3.01, and then closer is 3.001. We can also, by doing those substitutions into the equation, we can see that the right-hand side approaches a value of 5. It would appear that since both sides approach 5, the limit is going to be 5. So it appears that the limit as x approaches 3 of the function is 5. Now I say it appears because really this tabular approach is a risky endeavor, because sometimes things can appear to be doing one thing when in fact they are not. You can help mitigate that by not always doing like this was always multiples of 1/10. Like if I did 3.1 and 3.05 and 3.007, that might help mitigate this effect. But still, a tabular approach is not going to be the most precise way to evaluate a limit. It is, however, one way that can help evaluate very easy limits. In class, when we get back together, we'll actually take some time to explore more complex equations than just x plus 2. But for now, we're just looking at the idea of a limit. In this case, example 4, I have the limit as x approaches -7 of some unknown function. So I don't even have an equation to plug into. But I've told you the values on the table, and within this table, it would appear as though the left-hand side is in fact approaching a value of 6, and the right-hand side is also approaching a value of 6. Now, this does not mean that g of -7 is equal to 6. G of -7 is equal to 6. We can't actually say that. It just appears that both sides are approaching the value of 6. The actual value is unknown. But what we can say is that the limit as we approach both sides of -7 is 6. Okay? And for a visual representation of what I mean why this is not allowed but this is, we can go back to the graph above. Here, the left-hand side and the right-hand side both approach the value of -3, but the function was actually evaluating at -5. So the black box of this table is like that -5. We don't know where it's at. So we can't say g of -7 is anything. We have no idea. But both sides, the left limit and the right limit, approach the value of 6. All right, now that we've hit the concepts, the rest of these examples should actually move pretty smoothly. The limit as we approach 2 from the left, well, as we approach 2 from the left, it appears as though the value is 4. Gets closer and closer to 4. As we approach 2 from the right, our value also gets closer and closer to 4. Because the left limit and the right limit both agree, then the two-sided limit is that value, 4. If they disagreed, we'd write does not exist. And then finally, y of 2, well, we can see graphically it looks like 4, we could also stick 2 into the equation. 2 squared is 4. All these numbers agree. Y is continuous at x equals 2. Okay. We could have used some pre-calculus knowledge and said y is a polynomial and therefore continuous everywhere. But somewhere along the way, somebody had to generate a reason why we're allowed to say that, and it's born out of showing continuity at all the values. If we were to take the same approach in this table, we evaluated 1.9 squared, 1.99 squared, 1.999 squared, and we see from the left-hand side we're approaching a value of 4. Likewise, on the right-hand side, we're also approaching a value of 4. So it would appear as though the limit as x approaches 2 from both sides of x squared is 4. The table shows it, the graph shows it, and we're not getting into the analytical approach where we look at the equations yet, but we will get there. Okay. Not much to add to this bottom diagram. I just want to reinforce the point that a limit exists if we approach the same value from both sides. So in this case, both sides were approaching the value of 5, so the limit as x approaches 3 from both sides is 5. And we're going to see on the next graph what happens when they don't approach the same value. So here I have a graph. Symbolically, or sorry, via an equation, we have the equation written here. The graph of that equation is represented here. The limit as x approaches 3 from the left, well, from the left we're getting closer and closer to a value of 4. We don't ever quite get there because of this open circle, but we get close to it. As we approach 3 from the right, we're going down this line and we get closer and closer to the value of 6. The left side and the right side disagree, therefore the two-sided limit does not exist. If they did agree, then the two-sided limit could exist. Because these numbers are different, h of x is not continuous. H of x is not continuous, which we can very quickly see visually, but not continuous at x equals 3. That's specifically where we looked. Okay. Example 7, we have a graph here with several possible spots to examine, so we're just going to work through this. Approaching 0 from the left, we get to a height of 1. Approaching 0 from the right, we get to a height of 1. Because the left and the right agree, the two-sided limit is 1. Now let's look at 3. Approaching 3 from the left, we hit a height of 0. Approaching 3 from the right, we hit a height of 0. Both sides go to a height of 0, so the two-sided limit is 0. Even though the function evaluates to -1 at that location, the limit is 0, because when we look at points arbitrarily close to that location on both sides of it, we are at a height roughly equal to 0. Now we're going to look at the limit looking at -2. So as we approach -2 from the left, we get up to a height of 2, or approach a height of 2. If we look at -2 from the right, we are approaching a height of -1. And because these two limits do not agree with one another, the two-sided limit does not exist. We're going to explore continuity more in future notes, but as a preview, this is called a jump discontinuity, obviously because we have jumped from one point to another. And this is considered a point discontinuity, or a removable point discontinuity. Sometimes it's called a hole. Okay. There are other kinds of discontinuities that we'll explore in future notes, but that's it for this notes section. So thanks for watching. Be sure to mash that like button, hit the bell for notifications, comment, subscribe, and have a good day.